Thanks a lot, Nicholas, and thanks again so much for inviting me to do this. It's really a treat to be back. It's great to see so many, familiar names in the participant list, and I just hope everyone's doing, as well as they can be in light of this sort of ongoing pandemic emergency, right? So with that, I'll get started. So this talk is going to be about the group credence problem, right? Which is a problem that I think, while not necessarily always going by this name, is sort of well known in the sort of formal epistemology and especially social formal epistemology literature, right? And here's a scenario to just sort of pump your intuitions about the kind of problem we're trying to solve. So we suppose that Alphonse and Belinda are rushing to catch a train from Amsterdam to Brussels. If the train leaves before noon, then they can walk to the station. Otherwise, they're going to have to take a taxi. So it matters to them whether this train leaves before noon or after noon, or at noon or after. Alphonse has credence 0.7 in the proposition that the train leaves before noon, and Belinda has credence 0.3, right? And so then the question is, as a couple, what is their credence that the train leaves before noon, right? And that's the sort of problem that we're trying to solve. We can state this a little more generally and a little more formally as follows. So we start with omega, a sample space, and this is just going to be a set of sort of mutually exclusive possibilities, possible worlds. A is going to be an algebra on that sample space, and F is going to be a partition of that sample space such that the partition is a subset of the algebra, right? Then we have a set of individuals, I. There's n individuals in the group. And each individual is going to have a credence function from the algebra into the unit interval. And this is going to entail for each individual a particular probability space defined with respect to that sample space and the algebra and their individual credence function, and an individual specific probability distribution over this partition. So with that all in place, we can define this group credence problem, which is given an input consisting of a quadruple containing the sample space, the algebra, the partition, and the set of individuals, each with their own credence functions, their own individual specific credal probability space, return an output group credence function from the algebra into the unit interval. And I should say, it's kind of standard terminology these days in formal epistemology. By credence, I just mean a sort of individuals' probability distribution representing their beliefs about the algebra. And indeed, their credence function is going to have to satisfy Kolmogorov's probability axioms, right? So I'm interested in the group credence problem for groups that share a data set, but there's a problem lurking here. And as a result, and I really do hope I get this presentation of this right, but this comes from a result from Philip Dawood, and which is summarized nicely in the technical report by Kinney and Lichtenstein. And this result, I think, creates a problem for solving this group credence problem for groups of Bayesian agents that share a common data set and are basing beliefs on that data set and only that data set. So I'll explain a little bit about how this goes. So we suppose again that the agent's beliefs are represented by this probability space. And then we have a sequence of random variables, theta 1 through theta n, each measurable with respect to that probability space, each with the same range representing outcomes. So this represents sort of basically a series of repeated, it might be sort of, observations of some system under study that can take, these random variables can each take a various value, and that denotes, the state of the system at that particular observation. And the agent's going to set their credence in any of these random variables, theta I plus 1, taking some value x, for any x in the range of those random variables, by conditionalizing on the outcome of all the previous variables, right? So this is the agent. When it comes time to have beliefs about the next observation, what the outcome is going to be, they conditionalize on all of the previous observations, right, in order to set that credence. We let pi x here be the proportion of random variables in that sequence with outcome x. And then one can prove that the agent's credence in the proposition that as the number of observations goes towards infinity, the difference between the proportion of times that this outcome x occurs and the average credence that they have in that outcome occurring at any given observation, that difference is going to go towards zero with probability one, right? So they, with probability one, they believe that as they make more observations and update their credences and assign credences to events, and as those events occur, the difference between the proportion of times some particular type of event occurs and their credence in that event occurring will eventually converge, right? And so the upshot of this is that Bayesian agents are going to have maximal belief that they are maximally well calibrated, right? They are going to believe that almost always, in the sort of formal sense of the proposition having probability one, that as they sort of collect more data and just use their Bayesian conditionalization, they will end up converging on the true frequencies, right? Now, why is this important to the group credence problem? Well, provided that all agents collect the same data, once that data starts coming in, no agent should be willing to adjust their probability distribution over future events at all based solely on some other agent's analysis of the data. The idea being, if I think I'm maximally well calibrated, and I think that my degree of belief in some event occurring in the future is 0.5, someone else who's looking at the same data comes to me and says, well, actually, I think it's 0.3. I'm just going to say, well, they must not be well calibrated because I'm definitely well calibrated. I assign it probability one. And so the way I'm assigning beliefs should be the best way of assigning beliefs. So I really shouldn't, care really what other agents in the group think if we're all analyzing the same data. We just stipulate that, I don't consider there being any possibility that anyone else in the group has sort of private data or anything like that. However, prior to data collection, a group of agents can still agree to a binding mechanism for aggregating their credences at some later point, right? So this is sort of like Ulysses and the Sirens and other sort of cases that emerge in dynamic decision theory and dynamic belief. You can say, look, I know in the future that we might all find this aggregation method suboptimal. But before we collect any data, let's sort of commit ourselves now to some procedure for aggregating our credences at some future date. And let's see if there are ways that we can define that procedure in a principled way that's going to get us maximally close to the truth. And so my concern here is with how to find such an optimal mechanism for this kind of aggregation, even though once agents start collecting the data, they'll regard the aggregation as suboptimal at that future point. So this is how I'm conceiving of the group credence problem, as this kind of ex ante methodology for aggregating our credences at some future date. Okay. So in the literature, as far as I can tell, there have been two main, I've got a comment here in the chat. Nicholas, what do you think? Quick clarificatory questions or no?
That is entirely up to you. If you open that can of worms, it's on your head.
You know what? Yeah, sure. Go ahead. Go ahead, Christian.
Yeah, just a very quick question. In your calibration formula on, I think, one slide before the previous slide,
yeah,
you assign, there it is, yeah. You use the credence function CR to assign a credence to a particular credence assignment being made. So the CR occurs also within the argument of the credence function. And so I just wonder whether the event of you assigning a certain credence is actually one for which the credence function is itself defined. That was the clarificatory question.
Right, good. So I take it there's going to be a random variable defined on measurable with respect to the sample space. And that's really what's returning this value here. But it's a good question. I have to think more about the formal details of how it all precisely works. But I take it that there's going to be a random variable that's just equivalent to this difference between the proportion and the credences that you would assign through updating on some particular conditionalization procedure, and that's how you sort of get this in. for that sort of second order credence. I suspect those details can be worked out, but it's a good question. But definitely the sort of, the result's still gonna hold that agents should have maximal belief that they're maximally well calibrated. It's just a matter of working out those specific details, I think.
Thanks.
Okay, thank you. And I'll do my best to monitor comments if more people have them, but do try and keep them brief because I sort of planned this for 45 minutes. Right. All right, so getting back to what I was talking about, to date, it feels like most of the literature on this is focused on what sort of mean to take in aggregating individuals' credences. So one option is the linear mean, and it's going to be the one I'm talking about more today. And this is the option where you take just the sort of standard weighted average where the weights are non-negative and sum to 1 of each individual's credence at each element of the partition. And that's how you form this group credence function. The geometric mean is a little more complicated, but here you're just taking the product of each individual's credence in each element of the partition, where each product is raised to some power that's different for each individual potentially and weighted, and that's the sort of weight given to the individual's credence. And then the whole thing is we take the kth root, and here the individual's weights have to sum to k, right? And so for a very perspicuous and really interesting comparison of these ways of aggregating credences and others, I direct everyone to Gohang's recent paper in Synthesis, which does a really good job of explaining the ways in which these different methodologies converge. So I'm not going to be talking so much about that here. Rather, I'm going to be thinking about means in a bit more general way. And the way that's going to work is just thinking about these two properties that any mean has to have. Because what is a mean? Well, it takes as arguments a set of real numbers and outputs a real number. And that function is going to have two properties. First, it's going to be homogeneous in its arguments to some degree alpha. Not going to worry so much about that here. And then importantly, it's going to have this min-max property, which means that the mean of some set of numbers is going to have to be between inclusively the minimum number in the set and the maximum number in the set. And this is sort of well known to anyone who's worked with means in any way, but it's going to sort of feature heavily in the overall argument, right? And in particular, I'm going to focus on two arguments from Richard Pettigrew and Sarah Moss, who both argued that from a veritistic or accuracy first perspective, a perspective that thinks that sort of the good making features of a credence function are just its proximity to the truth. Then we ought to solve the group credence problem by taking a linear mean. And as far as I know, veritists sort of tend to support linear means for roughly these kinds of arguments that are given by Pettigrew and Moss. And yet, as I'll argue here, it remains the case that linear means are still highly inaccurate, right? It's still the case that in some cases, if all agents in the group have highly inaccurate credences, then any linear mean of their credences is going to be highly inaccurate because of the kind of min-max constraint introduced on the previous slide. And so what I'm going to argue is that stacking, which is a cross-validation technique from machine learning first developed by David Wolpert in the 90s, is going to outperform a linear mean in just these kinds of cases. And I'll say more about how that works. And I'll actually propose stacking as a more general methodology for aggregating group credences. Right? So here's the plan for this talk. I've just done a kind of extended background on the group credence problem. I'll then be giving some background on accuracy and inaccuracy measures, talk about the cases where a mean fails to be accurate, show how in such cases stacking can enable accuracy, consider and respond to Pettigrew's argument, consider and respond to Moss's argument, respond to some other counter arguments that I've thought of, and then finally conclude. Right? So here's some brief background on accuracy. So we're going to be talking really in terms of inaccuracy measures rather than accuracy measures, but obviously one is going to be just the mirror image of the other, right? So what is an inaccuracy measure? Well, it's a function that takes as its arguments a credence function defined on some algebra on a sample space, a partition of the sample space over which the credence function is defined on an algebra thereon, and an event, which I'm calling f dagger, which is stipulated to contain the actual world. We can call this the true event or the actual event here. And with these three inputs, it outputs a real number. There are two really popular measures of accuracy, of inaccuracy, probably well known to most in this audience. The first is the Breyer measure. And for the Breyer measure, we define a truth value function on the partition such that it returns 1 for the true element of the partition and 0 otherwise. And then the Breyer score is just the uniform average of the square difference between the credence assigned to each element of the partition and the truth value of each element of the partition, where 1 is true and 0 is false. So this is just the mean Euclidean distance between the credence function and this sort of omniscient credence that would assign 1 to the true element of the partition and 0 to all the others. Logarithmic measure is even simpler. Here, we just take the negative natural log of the credence assigned to the true element of the partition. And once we've defined things in this way, we can define the expected inaccuracy of a credence function according to some probability distribution defined over the same sample space in algebra. And this is just given by the equation, which is just the weighted sum of the inaccuracy of the credence function for the partition when each element of the partition is stipulated to be true, where the weights are given by the probability distribution over the partition. And note that the probability distribution that we're using to calculate expected inaccuracy of a credence function can be different from the credence function whose inaccuracy we're measuring or taking expectations of. And that'll be important in my subsequent argument as well. Okay. So what are some cases where a mean is not accurate? So I should say these cases are inspired by some work in the statistics literature by Merlis Clyde and Edwin Iverson. And let's suppose now that Alphonse and Belinda are reading reports that say the number of lynx and hares observed in an area of forest on a given day. It's just a very simple toy model. Each day's report is going to be a pair LH, where L is the number of lynx and H is the number of hares. The first 4 days produce a data set of reports, such that on the first day we have 1 lynx and 5 hares, on the second day 2 lynx and 11 hares, on the third day 3 lynx and 17 hares, and on the fourth day 4 lynx and 20 hares. And we're just going to stipulate that the true data generating process here is this model MT, according to which there should be 5 hares in the forest, 1 hare in the forest for every 5 lynx, or 5 times as many lynx as hares, plus some error term, right? Where this error term is going to be normally distributed about 0 with a standard deviation of 4. My choice of standard deviation here is really just done for mathematical tractability. It's not essential to my argument that standard deviation take any particular value. And indeed, when we compare multiple models, it's not essential to my argument that they all have the same standard deviation, even though I will assume that just for tractability's sake. Now we suppose that Alphonse and Belinda both have learning algorithms from the set of all possible finite data sets, where we stipulate that each data set, the data sets are going to have cardinality V, where V can change for different data sets. And M is the set of all signal noise models of this form, Fx plus epsilon right here. So all models of the form that take as their input the observation and return an outcome, and then add some error to that, add or subtract some error to that. So what is a learning algorithm? It's a function from sort of data space into model space, right? However, let's suppose in this case that Alphonse and Belinda both have very poor learning algorithms, such that from the existing lynx hare data, they output the following models. Alphonse thinks that there's going to be 2 hares for every lynx observed in the forest, plus the error term. And Belinda thinks there's going to be 3 hares for any lynx observed in the forest, plus the error term. And so Alphonse and Belinda in this case are both going to be sort of way off, right, from the true model, which is this H equals 5L model. And now let's suppose that on the 5th day, 5 lynx are observed. Let omega be the set of natural numbers with A the power set on omega. And we're going to partition omega into this set that contains, all the worlds in which less than 10 hares are observed on a given day, and all the worlds in which 10 or more hares are observed on a given day. I'm assuming here that the sample space is partitioned, is a partition on a set of possible worlds that just cares about how many lynx are observed on the 5th day, right? So with that partition, we can take some integrals and derive from their signal noise models their credence functions over this binary partition H. And what you get is that Alphonse thinks that the probability that there's less than 10 hares observed in the forest is 0.44, and the probability that 10 or more hares are observed is 0.56. Belinda thinks the probability, her credence that less than 10 hares are observed in the forest is 0.08, and her credence that 10 or more hares are observed is 0.92, right? But of course, if we were to derive a probability distribution from the true data generating process, we would get very different results, right? So if we use the true data generating process to derive probabilities, we see that the true probability that 10 or more less than 10 hares are observed in the forest, very close to 0, 0.533 times 10 to the negative fifth, and the probability that 10 or more hares are observed in the forest is very close to 1. And this is borne out in the calculations of expected inaccuracy. So by the standards of the true probability distribution, in the worst case scenario, a mean of Alphonse and Belinda's credences, it's going to have a Brier score of 0.394, expected to have a Brier score of 0.394 and a logarithmic of 0.587. In the best case scenario, sort of minimally inaccurate mean of Alphonse and Belinda's credences, by the lights of the true probability distribution is still going to have a Brier score of 0.014 and logarithmic of 0.088. So getting better, right? But of course, by its own standards, the true probability distribution is expected to have much lower inaccuracy, right? Very close to 0 on both measures, right? So this demonstrates that in these cases, the mean of any mean of Alphonse and Belinda's credences as compared to the true distribution is going to be quite inaccurate, right? So how can stacking enable accuracy in these kinds of cases? First, we better say what stacking is, and I'll say sort of explain stacking by sort of outlining what the goal of a stacking procedure is. So the group here is going to start with a common data set of pairs x1, y1 through xv, yv. I should say that in general, these x terms, the observations, can be vectors rather than individual real numbers. For the sake of tractability, I'm just making them all real numbers. And then the y's are going to be the outcomes. Each individual is going to have a signal noise model derived from the particular data set of the data generating process. So this subscript D here on the function that they use to predict outcomes given observations, that indicates that this model was derived by the agent's learning algorithm from the particular data set D. I just indicates that it's derived using individualized learning algorithm. And again, there's some error term added here. The goal of stacking is to find a weight vector such that the stacked model, which is built by aggregating using that weight vector, doing a weighted sum of each individual's signal model from the data, given that they are indeed individual I, plus the error term, right? So we're trying to find the best way of doing a kind of linear aggregation of the individual's models. And what's important here is that these weights, this weight vector, need not be positive or summed to 1. So we're opening up a much larger space of potential aggregations for solving this group credence problem and for sort of aggregating individuals' beliefs than is possible when we restrict ourselves to a mean, right? Now, moving a little further, we're going to do some cross-validation, right? So here we let D minus alpha denote the data set with the alpha data point removed. So we're holding out one observation within our data set. And then we can train each individual's learning algorithm, or rather each individual can train their learning algorithm on the data with that data point, that alpha data point held out, and arrive at a different model. And here we use this superscript minus alpha just to denote that this is the model arrived at when we've held out the alpha data point. And this expression here is just going to be the predicted value of the outcome, y alpha, when x alpha, y alpha is left out of the data set, but we're given x alpha as input, right? So if we were to take the first data point out, this is just going to be the agent's prediction, the individual's prediction, given all other data points of what that first observation should be, presuming that they didn't know it, right? And so for each individual, we can construct this leave alpha out vector, which is just a vector such that each of their entries is their prediction of the alpha data point when that data point is left out of the data set. So here we have their prediction of y1 when x1, y1 is left out of the data set, and they're given x1 as input, all the way up to their prediction of YV when XV is left out of the data set, but they're given XV as input. All right. Finally, let's let Q be n by n matrix such that each entry QKL is given by the following formula. It's just the dot product of individual K and individual L's leave alpha out vectors. And so what Q is a matrix in which each entry takes the dot product of two individuals in the groups leave alpha out vectors. And the diagonals of that matrix is going to be each individual's leave alpha out vector, the dot product of itself, right? So the diagonals is just going to compare each individual's leave alpha out vector to itself in that case. Now we let Y be just the vector of actual observed outcomes, Y1 through YV. And then we let C be a vector containing the dot product of the actual outcomes and each individual's leave alpha out vector. So for the first entry in C, we compare using the dot product, the vector of outcomes and of actual outcomes, right? So what's actually observed, and individual one's prediction of what should have been observed when each data point is left out of the data set, and so on for each individual's up towards n. I should say that, you know, I'm laying this out to sort of show how it's done. And in the next slide, we'll see that when we arrange things in this way, we actually get a sort of very elegant statement of the sort of solution to the stacking problem, but it's not important to really get into the details of how these matrices and vectors are built for this talk. All right. Having said that, we do now get to this proposition from Ley and Clarke, which is, I think, pretty cool. So for any data set and any set of individuals with their leave alpha out vectors, the weight vector that uniquely minimizes the sum of the squared differences between the actual observation, Y alpha, and the predicted value of Y, the predicted observation for each data point alpha, according to a weighted sum of each individual's prediction on that cross-validation scenario. The weight vector that uniquely minimizes that difference between observations and predictions when aggregating everyone's signal model is this vector that's just the inverse of this matrix Q that we defined times this vector C that we defined. So what this gives you is just with, you know, a little bit of linear algebra, a little bit of transformation of each individual's predictions that you can do in, you know, like 5 lines of code, what you get is a very simple statement of the weight vector that's going to uniquely minimize the difference between actual outcomes and predicted outcomes, where we're doing a linear aggregation of each individual's prediction for each cross-validation scenario. And this has, I think, an important implication, which is here we let fancy P be a probability function on all possible data sets. So here, you know, we're explicitly defining a different probability distribution in order to make these sort of second order kind of meta level claims about the effectiveness of this learning method. And let that probability distribution be such that all finite permutations of any data set have equal probability, i.e. all observation sets are what's called exchangeable, right? And this is a common assumption in a lot of this sort of inductive literature. By the law of large numbers, that the probability, according to this probability function, that in the infinite limit of data collection, so as the number of data points goes towards infinity, the average square difference between the actual observations and the predicted observations for each sort of cross-validation scenario, for each data point that could be held out of the data, is going to tend towards 0 with probability 1. And what this means is that in the infinite limit, we should expect the learning algorithm LS, which is a learning algorithm that first takes each individual's learned signal noise model and then aggregates them using this weight vector from Ley and Clarke's result. We should expect such an algorithm to yield highly accurate results. We should expect stacking to yield highly accurate results. And indeed, if you think about the sort of next observation in a data set as just a cross-validation scenario where that's the observation being held out and all the past observations are the ones that you have at your disposal, then this should enable us to get accurate predictions as well. Of course, that exchangeability assumption is important. That's why we haven't sort of solved the problem of induction with this stuff. But nevertheless, there's a salient set of cases in which we can use this methodology to get highly accurate predictions, right? Or at least as accurate as possible, right? We can sort of deploy this method on Alphonse and Belinda's case. So let's suppose that Alphonse and Belinda's learning algorithms produce the following leave alpha out vectors. So Alphonse thinks that on the first day there should be 3 hairs observed, on the second day 4, on the third day 6, and on the fourth day 7. Belinda thinks it should be 4, 5, 9, 11. But of course, these are both still highly inaccurate. And these, by the way, these numbers I just came up with by stipulation, right? They're not derived from anything. But they're meant to be sort of roughly in keeping with Alphonse and Belinda's overall derived learning algorithm from the full data set. And moreover, they're still highly inaccurate, right? So on the true model, which is this H equals 5L model, it should be the case that we expect to observe 5, 10, 15, 20 hairs in the forest, right? Using Ley and Clarke's results, we can derive the stacking weights 0.74 and 1.35, and notice that these stacking weights don't sum to 1. Indeed, there are other scenarios where they might not even be positive. And so we're sort of using that much larger space of aggregations to our benefit here. This gets us this stacked model where we multiply the weight vector by the vector containing the individual's predictions, and we get this result that the stacked model is one such that you should expect there to be 5.53 hairs for every lynx observed in the forest, and then we tack on the error term. So this isn't perfect. It's not getting us all the way to the true model, but it's getting us much closer than any sort of mean of Alphonse and Belinda's models could do. And when L equals 5, the group credence based on this stacked model is such that when we derive this credence, this group credence, the credence that there should be less than 10 hairs observed in the forest is very close to 0, relatively speaking, and the probability that there are 10 or more hairs observed is very close to 1. And we can see when we compare the best case scenario for Alphonse and Belinda, a mean of Alphonse and Belinda's credences by the likes of the true model, plus when we compare that to the stacking derived group credence, the expected inaccuracy of that credence by the likes of the true model, we see that we get much lower Breyer and logarithmic scores and much closer to the sort of best case scenario, which is the expected inaccuracy of the true model by its own assessment, right? And so what this shows is that we've been able to derive a much more accurate credence using stacking rather than taking a mean, right? So turning now to Pettigrew's argument, in this recent paper, Richard Pettigrew argues that a group credence problem ought to be solved by taking a linear mean of individual credences. And he says that this argument ultimately comes from a veritistic or accuracy first motivation, an accuracy first idea of epistemic value. So in light of the previous results, it seems, a bit of a head scratcher, right? That, on the one hand, it seems like stacking is able to get us more accurate models. On the other hand, there's this argument that from an accuracy first perspective, you ought to take a linear mean, right? So what's gone wrong here? So what I'll do is reconstruct Pettigrew's argument. First, we'll let a scoring rule be a function such that for a given element of the partition and a given credence function over that partition, the scoring rule takes this as its input the truth value for the partition and the credence for the element of the partition and the credence for that element, and returns a value between 0 and 1, right? So it's just taking the truth value, the credence, and giving you a score between 0 and 1. A scoring rule is going to be strictly proper if and only if for any element of the partition and any 2 credence functions, the average score for one credence function over both the case where the element of the partition is true and the case where it's false, as averaged by the probability assigned to that element by the other credence, is going to be uniquely minimized when those 2 credences are the same, right? So basically no credence function expects some other credence function to do better than it, right? And I'm not going to dispute anything about strict propriety here. I'm also not going to dispute anything about continuity, which is just the formal requirement that the scoring rule is continuous if and only if for any element of the partition, no matter the truth value of the element, the scoring function is going to be a continuous function of the credence assigned to that element of the partition. That's not in dispute either. What I will dispute here is this unanimity constraint. So what Pettigrew says is that a group credence is unanimous if and only if for any other credence and all individuals in the group, every individual thinks that that credence will have lower inaccuracy than the other credence, right? So unanimous credence is one such that all individuals expect it to have lower inaccuracy on average than any other credence, right? And what Pettigrew proves is that if inaccuracy is measured by taking a sum of strictly proper and continuous scoring rules, and indeed both the prior and logarithmic scores are such a sum, then any solution to the group credence problem that's not a linear mean of individual credences will violate unanimity. So you'd better take a linear mean if you think that unanimity is an important constraint on a solution to the group credence problem, right? And indeed, the stacking-based credences that I derived in the previous section violate unanimity, right? So looking at this table, we can see that Alphonse thinks that there's a mean of his and Belinda's credences that has lower expected inaccuracy on both scores than the stacking derived credence, right? And the same holds for Belinda, right? She too thinks that there's a mean of her and Alphonse and Belinda's credence models that derive a credence from that's going to do better than the stacking based one, right? And so a veritistic defense of stacking, which is what I'm trying to provide here, is going to have to say something about why unanimity need not hold, right? And what I'm going to say in response is that ultimately I think unanimity is not veritistically motivated, right? So I think unanimity is a really good constraint on a group credence problem if you have a commitment to both the claim that epistemic value of a credence function is solely a function of its accuracy, and that group credences should be arrived at through some procedure of deliberative democracy. There should be some process whereby when we come to the group credence, each individual can see themselves reflected to some degree in that individual credence, or even weaker, at least some individuals can see themselves reflected to some degree in that group credence, right? I think the second claim has a lot of virtues, and I think, in practice, if a bunch of people were trying to aggregate their credences, there might be all sorts of good reasons for doing this. But ultimately, I don't think those reasons have anything to do with accuracy if all members of the group are sufficiently inaccurate, right? And that's always, of course, a live possibility in these kinds of cases. And so from a purely veritistic, and I'd add probably quite externalist perspective in that it's saying that part of the justification for holding a credence, whether as a group or an individual, is going to come from what actually just sort of happens out in the world, independently of anything that we think about when we assign that credence. We should reject unanimity, I think, and embrace stacking, right? If we're trying to think just in terms of what the veritist should say about the solution to the group credence problem, right? Responding a little more quickly to a similar argument by Moss. So she also starts from the idea that the inaccuracy measure has to be a sum of strictly proper scoring rules. And then she presupposes that the expected inaccuracy of the group credence by its own lights has to be equal to some linear mean. These weights have to be positive and sum to 1 of each individual's expectation as to the inaccuracy of their own credence function, right? And under these conditions, any group that minimizes expected inaccuracy by its own lights must be a linear mean of individual credences, right? So if you're trying to minimize this function here, you'd better have a linear mean of the individual credences when you make the group credence. I've got a very similar response to this, which is that minimizing the expected inaccuracy of the group credence as determined by that group credence rather than by some sort of true probability distribution, by which I mean not necessarily an objective chance, but the probability distribution derived from the true model. This is only going to be a worthwhile goal, veritistically speaking, if at least some group members have accurate credences. And by contrast, Stacking is going to permit credences that will converge on the truth in nearly all cases under the assumptions of exchangeability, et cetera, right? So that seems to suggest that from a veritistic perspective, rather than taking a linear mean, as both Pettigrew and Moss have argued, we ought to instead do stacking, right? Now, respond quickly to some other counterarguments. So both of these counterarguments are going to be motivated by the fact that, the stacking proposal, this proposal for how to solve this group credence problem, requires that all individuals in the problem, sort of party to the problem, have a shared data set, and that's the only data they have, and learning algorithms mapping all possible data sets to the space of signal noise models. I think this raises two possibilities. First, there's the counter-argument that stacking to solve the group credence problem endows agents with an unrealistic level of epistemic ability. It's just unrealistic to think of agents as coming with these learning algorithms to find over all possible data points and all having, a perfectly mutual set of data. And the second counter argument is that in many cases, the agent's credences are going to simply be opinions, not derived from any data analysis. And the thought is we'd like the solution to the group credence problem to tell us something about how to aggregate those credences in a veritistic way, right? In response to the first argument, the idea that I'm over-idealizing epistemic life here, I think formal epistemology already represents agents in ways that idealize from epistemic life. You've got an exhaustive partition of possibility space, a full algebra on that space, precise numerical credences assigned to each element of the algebra. And I think, I would argue none of this implies that formal epistemology offers no normative guidance to agents. Rather, on the contrary, I think it's in virtue of its ability to idealize to some degree that formal epistemology offers some normative guidance, right? And in this sense, there's an analogy with scientific modeling. The useful models all have to involve some level of idealization. I think the same is true here, although there are, of course, interesting differences between modeling in formal epistemology and modeling in science. And for that, Joe Russos, I know, has given a number of talks and is probably working on a paper now that goes into really great detail and all that. And so with this all said, we can just say that adding the stipulation that agents have learning algorithms is just a difference in degree rather than kind, is sort of how we're formalizing the process. Right. Now, in response to the second counter argument, that sometimes credences are just opinions, not based on any analysis of data. Well, in that case, I think there's no reason to think that any mathematical operation on the group credences will result in, what I should say is significantly greater accuracy. Because there are results showing that, we can do better on average by taking a mean of individuals' predictions than by randomly picking some prediction. And so, there is some reason there to suggest that taking an average is still good, but still, that linear mean versus a randomly selected prediction from the group, those could both be really inaccurate, right? And so I don't think that when agents' credences are mere opinions, not based on anything, we should sort of expect some aggregation procedure on them to get really accurate credences. And in fact, you can, if you just think about this, I think that, if neither of us is a meteorologist, neither of us has been observing the weather in a place for any amount of time. And I think, there's a 0.3 probability that it's going to rain, in Istanbul tomorrow, and someone else thinks it's 0.7, but none of us really knows anything about that system. Then it's not clear to me that there's anything we can do with our credences that we should expect to get us closer to the truth, right? And what I think this reveals, which I think is a kind of sort of, I think, a cool subtlety of all of this, is that when agents have reasons, even bad reasons, that motivate and justify their beliefs, accuracy-enhancing methods of creedal aggregation are possible, right? As long as we're basing our credences on some model of the underlying system, even if it's a really bad model, we can then take those models and take the data and use procedures that will get us a model that's quite close to the truth, or as close to the truth as we can get under some assumptions. And I think this suggests a point of conciliation, a slight conciliation between epistemic consequentialists and non-consequentialists, for example, someone like Salim Berker, right? So the non-consequentialist is going to say that ultimately the source of value for an epistemic state is something other than its closest to the truth, but rather maybe something like the reasons that the agent has for holding the beliefs that they do. Whereas the consequentialist naturally is going to care about closest to the truth. There's a sort of caricature of the epistemic consequentialist that just sort of says, well, you know, if someone were to just sort of give you a pill that all of a sudden enables you to have true beliefs, then those beliefs have really high epistemic value, even though you've got no real reasons for holding them that are at least internal to you. Whereas the non-consequentialist is going to say that they are not sort of subject to that conclusion. I think what the consequentialist can say in response is, in light of these results, that in at least some scenarios, you know, you'd better have reasons. They need not be good reasons. And the reason for having reasons for your epistemic beliefs is not that that gives them epistemic value on their own, but that those beliefs can then be aggregated in such a way as to generate valuable beliefs in conjunction with the beliefs of others. So I think that interplay between sort of non-consequentialist and consequentialist approaches to epistemic value, in light of these results showing that even agents with bad reasons for their credences can be aggregated so as to arrive at a credence that is good by consequentialist lights, is, I think, worth pursuing in more detail. So with that, I'm just about at time, so I'll conclude by sort of summing up a little bit and talking about sort of future directions. So the group credence problem, I think, is now quite well-traveled territory in formal epistemology. And to date, as far as I can tell, the debate is largely centered around what sort of mean credence to take. What I've argued that is from a veritistic perspective, when individuals in a group share a data set that's sampled from a distribution that satisfies exchangeability, so a fair amount of background assumptions being built in there, stacking is going to be a preferable alternative to any averaging process, right? And where do you go from this? Well, I'm hoping to do some more work in the future, bringing these kind of stats, machine learning, sometimes what's broadly called just sort of the study of prediction. I think both Tri-Lee and Bertram Clarke, whose result I'm drawing on here, they describe themselves as really interested in prediction more than any other field. I think we can bring some of this work to bear on formal epistemology. I think it's quite close to formal epistemology, and it'd be great to get these two literatures talking to each other a little more. I'm also interested on the foundations of induction via cross-validation. You know, is there some deeper sense we can point to show why it is that cross-validation techniques like stacking enable us to do so well under certain constraints? And then finally, sort of going all the way back to the beginning of the talk in sort of thinking about this argument and thinking about the conditions under which the group credence problem even makes sense, I think it's interesting to think about the relationship between calibration and the dynamics of group belief and the way that sort of temporal or sequential considerations come into play there in terms of when aggregation procedures get decided, how they get decided. You know, another alternative that I haven't explored here is, instead of sort of making an ex-ante plan to aggregate our credences that we all deem to be suboptimal, at some future point in time, we could also all agree to forget a certain amount of data so as to then make aggregation seem like a rational and promising prospect for all of us. So I think teasing out all the ways of doing that would be very interesting in terms of more future work, right? But I'll stop there for now, and thank you all very much for listening.